In this video, we're going to walk through two volume problems. One is a volume of revolution and the other a volume of a cross-section. And we're going to use the same function for both. We're going to compare and contrast the problems and see how they are both similar and different from each other. So to take a look at both problems first, we've got the function f of x equals the square root of 2x plus 1. We're going to calculate the volume if we rotate it around the x-axis. And we're going to do this over the interval from 0 to 6. And then in the second problem, we are instead told that the cross sections are squares and that the side length of the square is represented by our function. And again, we want to find the volume from 0 to 6. Step one of our problem is to graph this function. So go ahead and pause and sketch a graph of this square root. So here I've quickly created a couple of graphs, and being super accurate on these graphs is not really all that important, but you do want to be able to get a decent visualization. So I know my square root graph has shifted to the left some, and then I've plotted the points 0, 1, and 6 root 13. Even having those coordinates is not necessarily important, but it can be useful for visualization purposes. So for the first problem, we're familiar with this. We're rotating it around the x-axis, and so we should graph the reflected part of our solid below. And notice we're only going from 0 to 6. I only really care about that section of the graph. And as these points spin around the x-axis, they're going to form circles. And we know that the radius of these circles is going to be determined by the function. So the radius is always going to equal square root of 2x plus 1 for each one of these. Now, to contrast that with the second problem, instead of spinning it around the x-axis, we are told that the side length of each square is determined by the function, and that the cross-sections are squares. In the rotation problem, our cross-sections, the cross-section just being what is formed when you slice this object vertically. The cross-sections were circles. But here we got squares, and we're being told that the function determines the side length of the square. So that's the side of the square. And now we can imagine the square being built off of the side really in either of two different directions. You can build that square towards you, or you can build that square away from you, and it's not going to matter either way. I like to build it and visualize it coming forward. So I'm going to draw kind of the other parts of my square, imagining that it's coming towards us in that third direction. And these squares are going to show up in lots of different places. And so we could get a visualization of a few of them. Maybe one at the beginning and at the end as well. Notice that once I get to the end, the squares are getting bigger because that side length is taller, whereas at the beginning the squares are smaller because that side length is smaller. We could even visualize what the connection is going to look like for this three-dimensional shape. And here's approximately what our three-dimensional shape looks like. Being able to create a sketch is useful. You will find as you do more of these, you may not need that sketch, but getting comfortable with these ideas helps if you can create a picture. Now with the first problem, we're comfortable with how we calculate this area. We know that we're starting from 0 and going to 6, and we know that the cross sections are circles, so we're going to do pi times our radius squared. And we would want to simplify before we do this antiderivative, so we're going to get pi times 2x plus 1, or if we want to write that as 2 pi x plus pi, maybe we would write that like that, 2 pi x plus pi. And then we just need to do this definite integral problem. So 2 pi x, that's going to become x squared, and dividing by 2, we're left with pi x squared, plus pi is going to be pi times x. We're going from 0 to 6, and so we get 36 pi plus 6 pi, which will equal 42 pi. And again, that formula is based on the fact that this is our radius, and we're going to do radius squared times pi because the cross sections are circles. So in our second problem, we've got cross sections that are squares, and the side length of those squares we know is equal to the function 2x plus 1. So then the question becomes, if I know the side length of a square, what is its area? Well, area is equal to the side length squared. So if I want to add up all of these squares, I'm going to go from 0 to 6, and I'm going to add up the side lengths squared, because that's the area of each of these squares. And so we could simplify just a little bit again, 2x plus 1, and do the definite integral here. We're going to get x squared plus x from 0 to 6, which gives us 36 plus 6, which equals 42. So our worksheet here has 4 more problems, and each one of these is going to describe to you the shape of a cross-section and a function that forms it. And so you're going to want to create a bit of a sketch of what the thing looks like. Imagine its cross-section, and then set up a definite integral that's going to allow you to add all of those cross-sections together. And different shapes are going to wind up requiring different formulas within that definite integral.